सर्वेभ्यः। अद्य सद्रत्नमालायाः सप्तमं सत्रं प्रार्थनया प्रारम्भं कुर्मः। वक्रतुण्डमहाकाय सूर्यकोटिसमप्रभ निर्विघ्नं कुरु मे देव सर्वकार्येषु सर्वदा। सरस्वती नमस्तुभ्यं वरदे कामरूपिणि विद्यारम्भं करिष्यामि सिद्धिर्भवतु मे सदा। अज्ञानतिमिरान्धस्य ज्ञानाञ्जनशलाकया चक्षुरुन्मीलितं येन तस्मै श्रीगुरवे नमः। ज्ञानानन्दमयं देवं निर्मलस्फटिकाकृतिम् आधारं सर्वविद्यानां हयग्रीवमुपास्महे। असाध्यसाधकस्वामिन् असाध्यं तव किं वद रामदूतकृपासिन्धो मत्कार्यं साधय प्रभो। किञ्चित् सद्रत्नमालायाः पूर्वकृतस्य श्लोकस्य पारायणं कृत्वा अग्रे गच्छामः। घनपरिकर्म व्याहृत् सीरी भाति शरण्यस्तत्पुरी गूढांग श्रीकृष्णः वीरोसावेकादि नवान्तं तुल्यस्त्यभ्यासोक्त घनस्यात्। अस्तु, ऑडियो इज नॉट वेरी ऑडिबल इति वदन्ति। इफ फॉर एवरीवन एल्स you face any audio issues? Okay. घनेत तन्मूलवर्गतदादि त्रिवधे ततः आदिवर्गान्त्यत्रिविधे युतेष्वङ्केष्वतो घनः। द्विधा कृतात्मात्मघातः त्रिघ्नस्तद्विघ्नान्वितः इष्टो नाड्यात्मात्मघातो वात्मनिग्नेष्टवर्गयुक् इति। एतत् एवं एतावता दृष्टवन्तः। इतः आरम्भं करोमि। गतवर्गे किञ्चित् घनपरिकर्म विषये तृतीयश्लोकतः आरम्भं करोमि। द्विधा कृतात्मात्मघातस्त्रिघ्नस्तद्विघ्नान्वितः इष्टो नाड्यात्मात्मघातो वात्मनिग्नेष्टवर्गयुक्। पदच्छेदः द्विधा आत्मघातः त्रिघ्नः तद्विघ्न अन्वितः इष्ट ऊन आड्य आत्मात्मघातः वा आत्मनिघ्न इष्टवर्गयुक्। एतत् एकमेव पदमस्ति, परन्तु अहम् अत्र किञ्चित् समासे अपि पदच्छेदं कृतवान्। तद् न क्रियते साधारणतया, तु अत्र स्पष्टतार्थं कृतवान्। अस्तु, अत्र द्विधा कृतात्मात्मघातः त्रिघ्नः तद्विघ्नान्वितः। अत्र द्विधा कृतं खण्डद्वयं कृतं। द्विधा आत्मनौ याभ्याम् अङ्काभ्यां द्विधा कृतं तौ। तौ अङ्कौ अत्र सूचयतः तौ अङ्कौ सूचयति। द्विधा कृतात्मात्मघातः द्विधा कृतात्मभ्याम् आत्मना च गुणितः। अत्र आत्मना गुणितः। त्रिघ्नः त्रिभिः गुणितः। त्रिघ्नान्वितः घनेन अन्वितः। तद्विघ्नान्वितः इत्युक्ते तयोः विघ्नान्वितः इति अर्थः। श्लोकस्य अर्थः कः? यद्येव उच्यते, यस्याः संख्यायाः खण्डद्वयम् अस्ति तस्याः गणः द्वाभ्यां खण्डाभ्यां त्रिभिः च गुणिता सा संख्या। अत्र द्वाभ्यां खण्डाभ्यां त्रिभिः गुणिता सा एव संख्या खण्डद्वयस्यापि घनस्य योजनेन लभ्यते गणः। अतः अत्र घनद्वयम् अस्ति। अत्र कः आशयः इति चेत् अत्र संख्या किञ्चित् बृहदस्ति चेत् तस्य किञ्चित् खण्डनं लघु संख्यया किञ्चित् खण्डनं कृत्वा एतत् किञ्चित् सुलभं भवेत् इति आशयः। So there's a bigger number, you just split it into two smaller numbers so that you cubing those two smaller numbers is easy, and then you add the multiplication of that with itself. इति तत्र द्वितीयः इष्टोनाद्यात्म आत्मघातः वा आत्मनिघ्न इष्टवर्गयुक्। अत्रैव एतदस्ति ऐडेण्टिटि तस्य प्रक्रिया. So previously we have seen a squared is a minus k times a plus k square. Just multiply that by the whole entire identity by a. You will get this one. अत्र पदपरिचयः अस्ति इष्टोनाड्यम् इष्टेन ऊनम् आड्यं च इष्टोनाड्यम् इष्टोनाड्यात्म इत्युक्ते इष्टोनाड्यम् आत्म. अत्र विशेषणपूर्वपदसमासः कर्मधारयः. आत्मघातः आत्मना गुणितः आत्मनिघ्नः आत्मना गुणितः इष्टवर्गयुक् इष्टाङ्कस्य वर्गेण युक्तः. अस्तु, श्लोकार्थः कः? वा इत्युक्ते अत्र इतोपि अन्या प्रक्रिया अस्ति इति. न्यू मेथड्. घनः संख्याद्वयस्य योजनं भवति. संख्याद्वयं तत् किम् इति चेत् प्रथमा संख्या इष्टेन अङ्केन ऊन. अत्र इष्टेन अङ्केन ऊन इष्टेन अङ्केन अधिका अमुकसंख्या इत्येतेषां गुणनसंख्या. अतः इष्टेन अङ्केन ऊन इष्टेन अङ्केन अधिका अमुकसंख्या. अमुकसंख्या इत्युक्ते संख्या यस्याः विषये वयम् इदानीं घनम् इच्छामः. द्वितीया संख्या का? इष्टाङ्कस्य वर्गेण योजनम्. इष्टाङ्कस्य वर्गेण योजनम्. अनन्तरं वर्गेण योजनं गुणनमपि अमुकसंख्यया गुणनमपि. अतः एतदस्ति घनपरिकर्म. अग्रे तस्य उदाहरणानि. द्विधा खण्डयित्वा घनः. अत्र 107 क्यूब्ड इति उच्यते. तावदेव अत्र. So this is 3 times the product of these two times the same number plus the cube of those two numbers. इष्टाङ्केन घनः अत्र 23 क्यूब् इति दत्तमस्ति. अस्तु, एषः घनः. इदानीं घनमूलस्य विषये पठामः. घनमूलं तु अद्यत्वे पाठशालायां न पाठ्यते एव. So it's not taught in the schools, in high schools. So please pay attention. In today's topic, a little bit it is maybe not taught in high schools. तर्हि घनमूलक्रिया अस्ति. घनमूलक्रियायाः कः प्रथमम्? अत्र प्रथमं दक्षिणतः वाम दिशि घनः अगनः अगनः घनः अगमः अगनः घनः अगनः इति यथा पूर्वम् अहम् उक्तवान् तथा अत्र अङ्कनीयं. वामतः गतौ वर्गस्थानानि अवर्गस्थानानि च अङ्कनीयानि इति. तत्र अघनस्थानद्वयम् अस्ति. तत्र प्रथम अघनस्थानः द्वितीय अघनस्थानः, प्रथम अघनस्थानः द्वितीय अघनस्थानः इति उच्यते तस्य अन्य नाम अपि अस्ति अन्यद् नाम आद्यः अन्त्यः अतः यदा वयं वामतो गतिं अनुसरामः तत्र प्रथमम् आद्यः भवति तदनन्तरम् अन्त्यः भवति अतः अन्त्यः आद्यः इति अन्यद् नाम अस्ति अथवा द्वितीयः प्रथमः इति अपि उच्यते गणितग्रन्थेषु अतः प्रथमं गणः अगणः अगणः गणः अगणः अगणः घनः अगणः स्थानानि घनस्थानम् अघनस्थानम् अघनस्थानं घनस्थानम् अघनस्थानम् अघनस्थानं घनस्थानम् अघनस्थानम् इति इदानीम् अस्माकं संख्या अस्ति एषा एतस्याः घनमूलं प्राप्नुमः वयं प्रथमं घनस्थानात् यावत् घनं यावत् यस्याः संख्यायाः घनं वयं शोधयामः so we have subtract the what we can the largest cube from this घनस्थान तर्हि तदनन्तरं तत् प्रथमफलम् अस्ति अनन्तरं शोधनीयं so you subtract it and you get the first difference so and take one digit each time that's what it is. So we put a number whose cube is subtracted so mark the number here and then take the next number tarhi idanim so atra you have to put this number 2 so you have to divide by 3 times the square of that number first placed up so divide by 3 times the square of that number tarhi atra 12 iti agachati so divide by 12 so what number do you have to divide by 12 you already have a set of digits here divide that number by 12 so basically you can divide 48 by 4 but if I if I have a remainder 0 I'll be left with 1 later I have to subtract a bigger number so I'm just dividing by 3 so it is 36 and remainder is 12 so dvitiyam phalam so you place that 3 here and you get one more digit so 121 you have to work with this number 121 so you have 23 and then now you have to subtract what do you have to subtract 3 times this number and then times the square of this number so 3 times 2 times 3 square you have to subtract 54 so how do you get that so you have to this 2 is corresponds to this 3 corresponds to this so 3 times 2 times 3 square so you have to subtract 54 so if you subtract 54 you get 67 then bring another number down now you have to work with this number tarhi now you have to subtract 3 cubed this 3 cubed subtract 27 you get 645 bring down another number so you have to work with 6459 so now you have to divide again so how it goes is subtract cube division subtraction and then division again after 3 times 23 square so 1587 is the divisor so then divide it you will get a quotient of 4 so you are left with 111 and bring down another number 1110 so this you have to work with okay so now you subtract 3 times 23 times 4 square so that is 1104 you subtract that number and then you are left with 66 and then you bring down the 4 then you have to subtract 4 cubed 64 0 so this ends the procedure basically here you always end this cube root by subtracting the cubed. So you cannot end in the middle. So if you end in the middle, the procedure is not complete. So this should be the completion step. Ataha. So just look at this. So basically, I'm ignoring the reminders and subtraction. Just showing the steps here. So subtract 2 cubed, divide by this one, and then 2 subtractions, and then the division, and then 2 subtractions. So that's how it goes. So this is the procedure. So now अत्र घनमूलकर्मणः क्रियावर्णनं प्रथमं किम् अस्ति? अन्त्यस्य घनस्थानस्य घनमूलं शोधनीयम्. अन्त्यस्य घनस्थानस्य घनमूलं शोधनीयम्. शोधितम्. अनन्तरम् अघनस्थाने क्रिया. अघनस्थाने का क्रिया अस्ति? अन्त्यात् अघनस्थानात् त्रिगुणितेन घनमूलस्य वर्गेण हरणम्. अत्र त्रिगुणितेन घनमूलस्य घनमूलम् अस्ति 2 इति संख्या. घनमूलस्य वर्गेण हरणं लब्धम् आदौ स्थापनीयम्. अस्तु. आद्यात् अघनस्थानात्. अत्र आद्य अघनस्थानात् किं क्रियते? त्रिगुणित घनमूलः लब्धस्य वर्गः च शोध्यः. अत्र त्रिगुणित घनमूलः लब्धस्य, अत्र यदि अत्र हरणं क्रियते तर्हि लब्धः इत्युक्ते कोशन् इत्यर्थः. लब्धस्य वर्गः च शोध्यः. अत्र त्रिगुणित घनमूलः लब्धस्य वर्गः च शोध्यः. अनन्तरं घनस्थाने का क्रिया? अत्र घनस्थानक्रिया अस्ति. लब्धस्य घनः शोधनीयः. एवम्. अतः लब्धस्य अघनस्थाने हरणं शोधनं, घनस्थाने शोधनं पुनः. अत्र घनः शोधनीयः सर्वदा. घनस्थानात् घनः एव शोधनीयः. अतः घनस्थानम् अघनस्थानम्, अघनस्थानं घनस्थानम्, अघनस्थानम् अघनस्थानं घनस्थानम्. अतः अन्त्यात् अघनस्थानात् हरणम्, आद्यात् अघनस्थानात् शोधनम् इति. तर्हि एषा प्रक्रिया अस्ति. तर्हि इदानीं पुनः एतत् क्रियते चेत् घनमूलं लब्धं भवति. अस्तु. तर्हि वर्गमूलस्य क्रियावर्णनम् इवेव अस्ति. वर्गमूलस्य क्रियावर्णने किं कृतं? वर्गस्थानात् शोधनम्, अवर्गस्थानात् हरणं, वर्गस्थानात् शोधनम्, अवर्गस्थानात् हरणं, वर्गस्थानात् शोधनं. परन्तु अत्र घनस्थानद्वयमस्ति. अतः पूर्वं घनस्थानद्वयम्, अतः हरणं शोधनं. वर्गस्थानात्, अत्र घनस्थानात् सर्वदा शोधनं. यथा वर्गमूले क्रियते तथा एव अत्रापि हरणं, परन्तु नूतनं किञ्चित् शोधनम् अस्ति तदेव. अतः किञ्चित् तस्य साम्यम् अस्ति इति कृत्वा अत्र स्थापितवान् वर्गमूलकर्मणः. अस्तु. तर्हि घनमूलस्य इदानीं श्लोकं पश्यामः. घनमूलस्य वर्गेण त्रिग्नेनाघनतोऽन्त्यः लब्धस्य वर्गस्त्रयादिघ्नः शोध्याश्चाद्यात् घनात् घनः. घनमूलस्य वर्गेण त्रिग्नेनाघनतोऽन्त्यः लब्धस्य वर्गस्त्रयादिघ्नः शोध्याश्चाद्यात् घनात् घनः. अत्र घनमूलस्य वर्गेण त्रिघ्नेन अघनतः अन्त्यतः लब्धस्य वर्गः त्रयादिघ्नः शोध्याः च आद्यात् घनात् घनः. तर्हि तत्र पदपरिचयः कः? त्रिघ्ने वर्गे इत्युक्ते त्रिघ्नेः वर्गे त्रिघ्नः वर्गः इति भवितव्यम्। अत्र परिष्करिष्यामि। त्रिघ्नः वर्गः इत्युक्ते त्रिगुणेभ्यः वर्गः। अघनतः इत्युक्ते अत्र अघनतः इति अस्ति, अघनस्थानतः इति अर्थः। लब्धम् इत्युक्ते हरणफलं, पूर्वमपि उक्तवान् हरणफलम् इति नूतनं पदमस्ति। लब्धं नाम हरणफलं, कोशेण्ट् इति उच्यते। त्रयादिघ्नः वर्गः, त्रिगुणितः आदिः वर्गः। त्रिगुणितः आदिः वर्गः। शोध्याः नाम शोधनीयः, घनात् नाम घनस्थानात्। आद्यात् नाम आदि घनस्थानात् इति अर्थः। अस्तु, तर्हि इदानीं श्लोकस्य अर्थः कः? अन्त्यात् घनस्थानात् घनः शोध्यः स्थाप्यः च एषः आदिः। त्रिगुणितेन पूर्वं स्थापितस्य घनमूलस्य वर्गेण अन्त्यः अघनस्थानतः विभजेत्। तर्हि घनमूलस्य वर्गेण अन्त्यः अघनस्थानात् विभजेत्। त्रिगुणितेन घनमूलस्य वर्गेण, यथा पूर्वम् उक्तवान्। अत्र पश्यतु, त्रिगुणितेन घनमूलस्य वर्गेण हरणम् अस्ति एव अत्र। त्रिगुणितेन घनमूलस्य वर्गेण अन्त्यः अन्त्यतः अघनस्थानतः विभजेत्। अत्र अन्त्यतः हरणफलस्य वर्गेण त्रिगुणितेन आद्यात् अघनस्थानात् शोधनीयः। आद्यात् अघनस्थानात् किं क्रियते? हरणफलस्य वर्गेण त्रिगुणितेन आद्यात् अघनस्थानात् शोधनीयः। त्रिगुणितेन पूर्वं लब्धस्य वर्ग घनमूलात् तत्र शोधनीयः। घनस्थानात् हरणफलं फलस्य घनः शोधनीयः। अत्र घनस्थानात् घनः शोधनीयः इति अर्थः। तत्र एवमेव उच्यते, पूर्वं यत् उक्तवान् तदेव। दिस् इस् ओन्ली एक्स्प्लेन्ड् हियर् इन् दट् श्लोक। Please, this might be a little bit going over the head, but please watch this video again so that you understand, because this is not taught in schools these days. There should be some typos here. Antyataha it should be. I will fix those typos. Haranapalasya vargena triguniteen adyat aghanasthanat shodhaniyah. So there are two things. So first is division and then subtraction. Just an extra step from vargamoolam. Astu. Tarhi इदानीं नूतन अग्रिमः श्लोकः अन्तिमः श्लोकः अस्ति। तस्मिन् विषये किञ्चित् वक्तव्यं मया। इष्टाङ्केन वर्गमूलस्य आवृत्तिक्रिया. So just the background, this is not seen in any of the other mathematical texts. Shankara Verma gives a very new technique to find the square root of a number in iterative fashion. So इष्टाङ्केन वर्गमूलस्य आवृत्तिक्रिया. आवृत्तिक्रिया इत्युक्ते इटरेशन् इति अर्थः। तत्र किमपि इष्टाङ्कं कमपि इष्टाङ्कं स्वीकृत्य वयं कर्तुं शक्नुमः. So this is a new methodology which Shankara Verma gives in his book, and somehow this is not known and this is not being popularized. I don't know why. So because it's not available in other texts and only in Sadratnamala it is available. So we will go through this. So let's say we want to find the square root of 625. So Ishtanka. So we choose any number, let's say 10. We divide that number, divide the number 625 by 10. So we get some quotient. We get some remainder. You take the quotient and then add that with the previous number which we chose. So this is any number 10. So take these two numbers and then find the average of it. And then take that average and then again divide the original number which you want to find the square root of. And then you get a quotient. So keep doing that. You find the divisor and the quotient, find the average of it, and then keep dividing the number which you want to find the square root of. Keep doing it. So here we have 36 and the quotient is 17. The remainder is some remainder. We don't even care about the remainder. So and then we get 17 plus 36. See, 17 plus 36 divided by 2. It's 26. And then you get another quotient. You keep doing it, you will get to a point where you'll just get same numbers. So 25 will be there, 25 there. After this, you will get a remainder of 0, and you will not be able to proceed any further because you have already hit the square root of the number. So let me go again. You take any number, and you could have chosen 2, 3 or something. Here, for simplicity, you've taken 10. So divide that number you want to find the square root of by 10, get a quotient. So now find the average of the quotient in the divisor. You'll get another divisor, 36. Again, find the average of the quotient and the divisor. Divide that same number, 625. You'll get another divisor and quotient. After some point, you'll have the divisor and the quotient to be the same. So the average will be the same again, and it is you would have found the square root. So this means that you have found the square root. Okay, so two things I have to tell you now. This works for perfect squares. So for non-perfect squares, we can extend this. We will talk about it. But this methodology works for perfect squares. And also now here, let's say here 53 by 2. The average is not a whole number. So we take the whole number closest to it, the floor of that. So for example, 26.5 is 26.5 is the divisor. Take 26, just the whole number part of it, and then keep dividing. So two things. So basically, when you find the average, take the whole number part of it and keep dividing. And we apply this technique for square numbers, perfect squares. So there is a question, isn't this similar to the so-called Newton-Raphson method for finding square roots? I think it is, but somehow I'm not recollecting what's Newton-Raphson method. Let's go with this. I think probably it is the case. I don't know whether it's called Newton-Raphson method or something. Okay. Okay, so अत्र पश्यन्तु इष्टाङ्केन वर्गमूलं यदि इष्टाङ्कः x0 भवति तर्हि अत्र so this another thing. So you have to choose this. How do you choose this number? The initial number is a very important criteria here. You can choose some random number. For example, you can choose like 2. So you'll go over a long time. If you choose a number which is if you guess the square root, let's say you choose 24 as this number, you'll immediately come to the answer very quickly. So depending on that you choose the initial value, you will do the calculation as many times. Okay. So answer question. इष्टाङ्केन वर्गमूलं यदि इष्टाङ्कः x0 अस्ति तर्हि एते अंकाः उत्तरोत्तरं वर्गमूलस्य अत्यन्तं निकटं प्राप्नुवन्ति. So what I'm saying is, if x0 is the initial value, then this sequence of numbers, what is the sequence? Xn plus 1. So if x is 0, x1 is half s. S is the number we want to find the square root of this. Half xs by x0 plus x0. This value will be the x1. Then x2 will be half of s by x1 by plus x1. So this is a sequence of numbers, and the sequence converges to s, square root of s. I mean, this is a very technical term. It converges means, so it goes very, very close to the square root of s. Is what it means. That's all. So if you don't know enough calculus, so don't worry about it. But this is a basic calculus, which says this sequence of numbers goes very close to square root of s. That's what it means. Okay, so let's dig this further, or let's understand this particular thing. So let's say I want to find the minimum of this function. X is now a real number, and for all positive values of x, we want to find this particular, in this particular expression, s is a square number. Let's say s is a perfect square, and we want to take this expression, a function of x in the continuous domain. So x is a positive number. You want to find the minimum value of this particular function. So whatever I'm going to say now, if you don't understand, don't worry. It's not important to understand, to do the homework or anything. This is just for some people who want to understand a little bit about this. Okay, so how do we find the minimum value of this expression for all positive values of x? So it's we can, I mean, if you know calculus, you can do this very simple, very easily. You just take the first derivative of this expression with respect to x and equate it to 0, and you will get a value of x which minimizes this particular function, and also we can find the minimum value of that. Okay, so let's take a different approach. So let's say x is, because x is positive, I can always write x as y square. So this makes it, because x is positive, I can always write this substitution. I'm going to just make it, and then I'm going to rewrite this expression as I want to minimize this expression for all positive values of y. So now this, if I write this way, it's much easier for me to look at what's the minimum value of this function. I can just write, rewrite this as I want to find the minimum value of all of this expression over all positive values of y. So this expression I have just written in a different way. I have done there's something called a completion of squares. So this is what it is. So now this is, by just seeing this expression, we can say that the minimum value of this expression is actually square root of s, because this sum of two positive numbers. So this is a square number. This is always positive, and this is square root of s, which is a constant number. So if you want to have the minimum value of this whole expression, I have to force this value to be 0. Otherwise, for any non-zero value, this will increase this expression. This value, this will have a positive value. So positive value plus positive value will be a positive value. So this, if I want to minimize this whole expression, I want to find the minimum value of this, I have to somehow force this particular number inside the square to be 0. So that can happen if I say square root of s by y is equal to y, right? If I want to force this to be 0, I make this equal to this, so then it will become 0. So that value means y square is equal to square root of s, but y square is x. So x should be square root of s. So if x is equal to square root of s, this entire expression will be the minimum value, and it will become the square root of s. Okay, so why did I say this? So then the point is, this minimum value of this expression is square root of s, and it occurs, and that point is at s, x equal to the square root of s. So somehow I think Sadratnamala, the Chandrasekharan Raman knew this, and he's giving a iterative solution here. I don't know, maybe a Newton-Raphson also. I have to take a look at what's Newton-Raphson method, but Chandrasekharan Raman is doing that, and it is not that Chandrasekharan Raman was the first one. Chandrasekharan Raman was the first one to do this. We will discuss more about this. So if you let me also show this. So if this expression, we can it quickly goes to the square root of s. I can also show you the graph of this particular thing. Show you. So here is the graph. I graphed this number f of x as half of 16 by x plus x. So this is this nice looking, well-behaved function, which is like a nice bowl kind of thing, where if you drop a ball somewhere, it will go and come and sit in the square root of x. So that's a stable point. So if you drop a ball, it will come down and like this, and then come and here, sit here properly. And this straight line is y is equal to x. So let's start from any point. So I'm starting from 10. So the value of, if I put x equal to 10, the value of f of x is 5.8. Then I move to, the next value of x will be y, right? I said, so y is what I told is, I keep taking the value of x to be the value of that function. So then I come here, and then the next value of x will be this point, which is 5.8. And then I move to the y equal x value, and then keep coming down, and finally I settle down at this point, which is the almost square root of x. So that's the algorithm which we are going to do in what Sadratnamala is, Shankara Verma is actually mentioning. So let's look at it. So अस्तु, इदानीं स्क्वैर् रूट् आफ् 2 इत्यस्य मानम् अत्र 2 इत्यस्य वर्गमूलं कथं प्राप्यते इति. Let's take the initial value. So s is equal to 2. We know that we want to find the square root of 2. So s is equal to 2. And let's take the initial value as 2. So if we start as initial value as 2, so x1 will be half of s by x0, which is 2. 2 by 2 plus 2. So that is 3 over 2. Now the second value x2 is actually, I have to take x2 is half of s by x1. x1 is 3 over 2. Half of 2 by 3 over 2 plus 3 over 2. So it will be 17 over 12. x3 is half of s by x2. 2 by 17 over 12 plus 17 over 12, which is 577 by 408. This particular thing is also seen in our this particular sequence of numbers is seen in the Shulba Sutras. Square root of 2 इत्यस्य प्रयोगः शुल्बसूत्रेषु बहुधा क्रियते. बोधायनः अस्य मानं कथयति. बोधायन शुल्बसूत्रे एतदस्ति प्रमाणं तृतीयेन वर्धयेत् तत् चतुर्थेन आत्मचतुस्त्रिंशोनेन सविशेषः. अत्र सूत्रम् एतदस्ति सूत्रम्. अस्मिन् सूत्रे रूट् 2 इत्यस्य मानम् एवम् उच्यते. 1 plus 1/3 plus 1/12 minus 1 by 3 times 4 times 34. अत्र अस्तु, प्रमाणम् इत्युक्ते किमपि मानम् अत्र एकम् इति स्वीकुर्मः. प्रमाणं तृतीयेन वर्धयेत्. तृतीयेन वर्धयेत् तत् चतुर्थेन एवम् अस्ति. तदनन्तरम् आत्मचतुस्त्रिंशूनेन सविशेषः. अत्र आत्मचतुस्त्रिंशूनेन तत् चतुस्त्रिंशूनेन सविशेषः इति. So he gives the value of square root of 2 as this expression: 1 plus 1/3 plus 1/12 minus 1 over 3 times 4 times 34 इति. एतेषां भिन्नसङ्ख्यानां फ्राक्षन्स् इति अर्थः. भिद्यते, संख्या भिद्यते खलु. So it is not a whole number, it is fraction. It's a fraction. अभिन्नसङ्ख्या नाम whole numbers, भिन्नसङ्ख्या इत्युक्ते fractions. एतेषां भिन्नसङ्ख्यानां सरलीकरणेन लभ्यते 577 by 408 इति. etadeva square root of 2 ityasya samipatamam manam bhavati. So what Sulbasutrakara is saying is 577 by 408 is a approximation of square root of 2. So if you want to find, it's an irrational number, so this is going to be an infinite series, but I'm going to cut it off at some point, and 577 by 408 is a good approximation of square root of 2. Sutre savisheshaha iti padam kinchit vilakshanam eva yataha anena asya praptasya manasya asannata dyotyate. Asannata ite nikate asti iti artha. So close by, being very close to iti artha. Arthat uktam manam sakshat tulyam nasti. Asya manam kayapi bhinna abhinna sankhya darshayitum na shakyate. So any irrational number you cannot give by a rational number. You cannot. The square root of 2 is an irrational number. I hope you all understand what an irrational number is. So an irrational number cannot be expressed in the form p over q, in a form of a fraction. So ataha asya manam kayapi bhinna abhinna sankhya darshayitum na shakyate. Square root of 2 ityasya aparimeyatvam. Ata irrational number ityasya aparimeyatvam avagatya tasya asannam nikatam manam kachitavantah bharatiya ganitagnaha. So people knew that square root of 2 cannot be exactly measured. So they knew about it. So what they did, so here they gave a kind of a approximation. So if you look at it, this particular thing, if let's say I didn't have this last term, the first 3 terms is actually 17 over 12. And the next term is actually making it even more precise, making it 577 by 408. So this is something called a rational approximation of irrational numbers, which is a very famous. If you read any mathematical about anything about Indian mathematics, this rational approximation of irrational numbers is something which Indians were very good at. So they really understood what is irrational number, and they tried to keep on giving good rational approximations for these irrational numbers, is what we understand. So this is Sulba Sutrani. Sulba Sutras are one of the very, very old works. So basically it is, I don't know, people keep telling it is 1500 BC or maybe even older. So Bodhayana Sulba Sutra, Apastamba Sulba Sutrani, etani santi. Ataha rational approximation of irrational numbers. So we started out with saying that Sadratnamala is giving some numbers are perfect squares and also only integers and all these things. Now we are already using that whatever Sadratnamala Shankara gave, we have already come to a rational approximation for irrational numbers. Okay, so this particular thing, hope you understood. So there will be a homework question on this. If you didn't understand, please come back and listen to this video. So, tarhi ishtankena vargamulam ghanamulancha ishtapteshtaikhyardhamishtavisishtam kruteh padam ghanamulam virapteshtayogartham avisheshitam. Ishtapteshtaikhyardham ishtavishishtam kruteh padam ghanamulam virapteshtayogartham avisheshitam. Padatyedah asti ishta apta ishtaikya ardham ishtavishishtam kruteh padam ghanamulam vihi apta ishta yoga ardham avisheshitam. Padatyedah. Astu atra eka prashna asti 577 by 408. When do we stop this iteration? If you want more precise numbers, you can keep on going. You need not stop this iteration, but you stop the iteration when you think that you have enough precision. So this approximation for irrational numbers has to be done even in today's computers, because computers also have finite register lengths. So they also store some only up to finite numbers. For example, if you want to store the square root of 2, you will stop at certain digit precision. It depends on what is the precision you want. So that's when you stop the iteration. That's the question. Will this method work for square root of 3 too? So that is the homework. Okay. पदपरिचयः आप्तम् इत्युक्ते लब्धं पूर्वमपि उक्तवान् इष्टभाजेन आप्तम् इष्टाप्तम् ऐक्यं नाम युक्तम् अत्र एडिशन् ऐक्यम् इति उच्यते अत्र नूतनं पदं सङ्कलनं युक्तं योजनम् इति सर्वम् ऐक्यम् इति सर्वं समानार्थकं पदम् इष्टेन ऐक्यम् इष्टैक्यम् इष्टाप्तेष्टैक्यम् इष्टाप्तं च इष्टैक्यं च इष्टाप्तेष्टैक्यार्धम् इष्टाप्तेष्टैक्यस्य अर्धम् इष्टविशिष्टम् इष्टमेव विशिष्टं कृतेः पदम् पदम् इत्युक्ते मूलम् इति अर्थः कृतेः पदम् इत्युक्ते वर्गस्य मूलम् इति अर्थः दिहि आप्त इष्टयोगार्थं द्विवारम् आप्तं च इष्टं च योजितं तस्य अर्धम् अविशेषितं शेषं विना अत्र प्रथमा पङ्क्तिः वर्गमूलं सूचयति द्वितीया पङ्क्तिः घनमूलं सूचयति so just as I previously mentioned so you take this अत्र इष्टाङ्केन वर्गमूलम् इष्टाप्त इष्टैक्यार्धम् इष्टविशिष्टं कृतेः पदम् अत्र नूतनम् इष्टं किम् इति चेत् संख्या संख्या इष्टेन भक्तम् अनन्तरम् इष्टं तेन योगः तस्य अर्धः तदेव इष्टेन भक्तः संख्या इष्टेन भक्ता संख्या इष्टेन योजितम् अर्धीकृतं च नूतनम् इष्टं भवति एवं पुनः पुनः करणेन इष्टं संख्यायाः वर्गमूलं भवति so this if you keep on doing this iteration this ishtam the sankhya will itself become the square root of that number will be the square root of that number घनमूलं दिहि आप्त इष्टयोग अर्धम् अविशेषितम् अत्र नूतनम् इष्टं किं द्विवारं यदि अत्र पूर्वं किम् अभवत् किं कृतं संख्या इष्टेन भक्तः आसीत् so it was divided once here if you divide by twice the same expression you will get the cube root इष्टेन द्विवारं भक्तः संख्या इष्टेन योजितम् अर्धीकृतं च नूतनम् इष्टं भवति एवं पुनः पुनः करणेन इष्टं घनमूलं भवति so that is he just extends it to the cube root also but here the cube root I think it works only for perfect cubes and also integers here so here ishtankena घनमूलस्य आवर्तिपक्षः so you just divide twice so first you divide I want 5 the square cube root of 512 so again choose 10 as the ishtankha so you divide by 10 and then you get a quotient divide that quotient again by the same number 10 you get 5 or you could have just divided 512 by 100 and you would have gotten 5 but keep rounding off then do it so again next is like you have 512 so you have this 5 and then 10 you find the average of it 15 by 2 and then 7 you again do this 512 divide 512 by 7 then you get a quotient divide that quotient again by 7 you get 10 so you get, and now you have 10 and 7 find the average of it 8 you have so 8 you divide once twice you get avisheshitam so you get no remainder so that's where you find the cube root that is a question can this be extended to the nth root yes it can be extended you can check in your spare time yes this algorithm can be generalized to any of the nth root we mean to divide the number n minus 1 times. Correct. That's correct. So that is the point here. But Sadratnamala does not say that, but we can infer that. Okay. So this is, I think this is not being taught in schools, and even I have not seen any. There are a lot of articles which keep bringing out that, okay, Indian mathematicians did this, that, and all this. Somehow Sadratnamala has not been really portrayed well and brought out well. I don't know why. So now that we are learning, please, you can use these techniques, or if you're teaching in schools, you can teach this to students of high school. This is very easy to understand for high school students, right? And it's quite a very fast convergence. It's not like it takes a lot of time. Yes, these things should be taught in school. Somehow I am seeing that the NCERT does not even teach cube roots in schools. Cube roots are now using prime factorization. So they factorize that number into primes, and then if there are, of course, there's a perfect cubes. So from the perfect cubes, from prime factorization, it's very easy to find the cube roots. So these are the things which has to be taught in schools. One of the things is that these make you think in terms of algorithms. So how next steps and all these things. So how do you write a methodology in steps? So later programming, when you're done programming a computer, writing in steps like this will help you to program a computer. And then after that, there are a lot of computer scientists who also find what is the how fast this methods converge, how fast you can get to the square root of or cube root and all these things. So that's a whole subject on its own. Okay, how about non-square and non-cube numbers? So one of the applications I already mentioned is the rational approximation for irrational numbers. That can be one of the methodology. So which you can use this for, at least for squaring square roots. We can use that methodology to find the rational approximation by irrational numbers if you are working only with fractions. Of course, if you the whole methodology here, which I mentioned here, this is also for work for continuous numbers. So if you are working in the domain of continuous numbers, you can find an iterative methodology to come to the square roots. Or if you want to work with fractions, for example, this particular numbers, here I will restrict myself with xn's as only rational numbers. You can get to the get closer to the square root with only rational numbers. So these are the things which I think these methodologies are available in Indian mathematics. But I mean, did they talk in terms of rational numbers, irrational numbers? That was not their. So their system was not based on that, right? So you can always define that, okay, this is an irrational number and all these things, and go forward with that. So there is a set of axioms, so whatever you can call. So the way they make their theory is based on what they have defined. So you will not find, okay, aparimeya sankhya and all these things in Indian mathematics texts. So they have their own way of defining some parameters. Okay, so that's what I have for today. So we are almost done. We are done with the first chapter of Sadratnamala. We will start with the second chapter of Sadratnamala from next class. If there are any questions, I can take. प्रश्नाः सन्ति चेत् अहम् उत्तरं दातुं शक्नोमि. प्रश्नाः सन्ति वा? पुनः तर्जयतु. Okay, actually I also tried to plot the cube, I'll show you that also. So this is how the cube looks. So here again, of course this value, the extremum is here, but still if you are working only with integers, you still get to this point, even though the minima lies here. And this is only for those people who want to have a geometric interpretation of this. But if you didn't understand this, it's okay, don't bother. But here, this particular iterative solution is very nicely, you can observe this here. Okay, yeah, currently this is called the staircase method. Yes, there are a lot of ways to iterative methodologies to find the square roots and all these things, but I'm very surprised that I didn't. This last particular shloka from Sadratnamala is not from anywhere, and generally Sadratnamala follows exactly what the previous mathematicians, and he very closely follows Aryabhata's verses. But the last verse was very eye-opening for me. So probably there are Indian mathematicians who knew this iterative methodology and for finding square roots. That's what I find. Okay, I didn't understand the last point by Anand Madhya. It's likely solution of two equations, x equal y and parabola or cubic. I didn't understand that. What was the context? If you want to talk, you can talk. Okay, if there are no further questions, we can end this class. Okay, the square root technique which is mentioned in Vedic mathematics. Okay, that's a question. Very good method. May I know how this method is different from the square root method, technique method mentioned in Vedic mathematics? So the square root technique mentioned in Vedic mathematics is very similar to the square root technique which is mentioned in the previous verses. Okay, let me show you that. So this is okay here. This is the square root technique mentioned in Vedic mathematics. If you know, it's very close to this. It's not much different from this, but it's not an iterative method. Of course, this is it's a long division method. This maybe you can call it a long division method. This is the method which is mentioned. The similar method is mentioned in Lilavati. A similar method is mentioned in Vedic mathematics book by Bharati Krishnatita Swamiji. It's a long division method. But what today I mentioned was an iterative method to find. You can start with any number and you can get to the square root of that number, which is not what Bharati Tirthaji mentions. Bharati Tirthaji's method also I like it much. It's a little bit better than this. You don't have big numbers. Maybe if I have time, I will also cover that. It's a little bit different than this. Okay. Is there a homework? That's a good question. So there will be a homework. So I will post the homework in a couple of hours or maybe in 4 or 5 hours today. So it will cover the rest of the portions in the first chapter. So maybe squaring, square root, cubing, cube root. So I will post by end of the day today for me. Okay, so being iterative, it is easier for computation. Correct. I mean, iterative is some, at least for computers, an iterative method is useful. You tell, okay, this step, go next step, like step by step you keep telling. Okay. अस्तु, तर्हि समापयामः. ओम स्वस्ति प्रजाभ्यः परिपालयन्तां न्यायेन मार्गेण महिषाः गोब्राह्मणेभ्यः शुभमस्तु नित्यं लोकाः समस्ताः सुखिनो भवन्तु. धन्यवादः.